My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar series on graphene and energy storage devices, including batteries and supercapacitors and all those different chemistries that are working on in this sector. I'm exceptionally pleased to have Professor Mark Copley from the Warwick Group at the University of Warwick, WMG at the University of Warwick. And with that, Mark, I'm just simply going to turn it over to you, introduce yourself, and then we're very excited to hear what you have to say, especially what's coming from your center, where you guys have a really good overview on the overall development of energy storage applications. Thank you.
Okay, thanks, Terrence. As has been said, I'm Mark Copley. I'm an associate professor here in the Electrochemical Materials Group at WMG, which is one of the bigger departments of the University of Warwick. I've been here for 2.5 years now. My group's main interests are in maximizing the performance of current lithium-ion, sodium-ion technologies. A lot of that on the focus on beneficial coatings on the active materials, also optimizing the formulation of slurries and looking at next generation processing technologies. I'm not a career academic. I spent 12 years working in Johnson Matthey prior to taking up a position here, very much based at the Technology Centre supporting what was then the Battery Materials Division. So working on current, but also future technologies through funded opportunities. So what I have is kind of a two-stage presentation, fairly short and snappy, I hope, and basically talk about some of the capabilities in general that we have here within the Energy Innovation Centre where I'm housed, and kind of then some comment and demonstrators on conductive additives and the benefit and the reasoning for why you might use them in slurry formulations. Okay, so just minimize this, if you give me, bear with me, thank you. So in terms of EIC Energy Innovation Centre, we're very much a cradle-to-cradle type of facility, looking at things from the raw materials through materials, electrochemistry, cell components, all the way up into pack, BMS application, and now setting up a pilot line for recycling as well. And the idea being sustainability, the recycling feeding back into the beginning of the raw materials. And I'm sure people have seen the 400 to 500% increase in lithium carbonate in 2021. So having to come up with ways of meeting these ever-increasing targets of reducing watt-hour per kilogram costs, nigh on impossible with ever-increasing precursor costs. So like I say, research challenges exist across all parts of the development cycle, also looking at scale-up. Very much our facility is the UK's scale-up facility with pilot line as well, which we'll touch on as we go forward, but it's kind of our differentiator from other universities in the UK. Just to kind of further expand on that, looking at the fundamental chemistry, the new materials, electrode innovation, process scalability in terms of mixing, coating, and assembly. It's not just about mixing it, it's about mixing it in a way that is scalable, all the way up to gigafactory. I like to look at the unique technical challenges, but to be able to solve them in a way that can end up being applied and working in the real world. In terms of battery characterization, we can cover the whole spectrum from your basic half cell to putting a nail through a pouch cell inside our abuse chambers. Multi-scale format, which is quite a unique capability for us, the coin, swage lock, L-cell 3 electrode, A7, A5 pouch, 18650, 21700 cylindrical, and the next line is out of date because now we have over 3,000 test channels. Also, as I was saying, pack, climatic testing. We're just about to bring in testing chambers to look at reduced atmosphere for aerospace applications as well. And as I said, the recycling and recycling and looking at pilot scale plants there as well. just a snapshot of what we have in terms of the battery scale-up unit here. So the kind of the life cycle, shall we say, of that. From the intake of powder to the mixing, this is shown kind of an old double planetary mixer. We've now evolved past that to much more high-speed mixers and able to make a slurry in 30 minutes now as opposed to 6 hours using this equipment. Able to do single-sided coating, rewind to double-sided, the thermal chambers for drying, calendaring, slittering, cell stacking, cell tab welding, packaging, electrolyte filling, formation and aging, and then end-of-life testing. So we have a separate facility for aging and degradation where the cells are left on for extended periods of time. And obviously, as I'm sure a lot of people on the call are aware, then looking at things like the amount of deep dive into the data from formation to end of life, and the information that can be got from that is far more than just a capacity number and a voltage profile. This is kind of going a little bit deeper into the different areas. So across electrochemistry, obviously discovery, synthesis, evaluation methods, electrode, electrolyte, a lot of interest evolving in terms of electrolyte, people looking at high voltage versus solid state and the economics involved therein. Additives is why I'm here to talk to people today. Coating, both the material and electrode structures, cell, all what you can see inside in there. Pack applications, then even how we integrate. We have a small amplify pack that was made and put into a small little Zoe type of vehicle, and then the second life recycling. And you can see at the bottom here that there is forms of modeling across most of the different interest areas for us. See how I'm doing here. Also, we have a forensic capability. So hyphenated glove box setup where we can do post-mortem analysis, failure modes, analysis of cylindrical pouch, hoping to expand that out to prismatic as well. And this would involve gas sampling, gas analysis, electrolyte analysis, able to work with other teams on site here too on the CT scanning. So able to simultaneously scan 6 21700s, deconvolute into each cell. And as you can see here on the bottom left, the imaging where again you can determine failure modes without having to even open the cell. Because I'm sure, like me, sometimes you worry that how much damage do you do in opening the cell to evaluate it. So we can actually go past that as well. And obviously a lot of in-depth XRD, inoperando, XRD, XRF, and microscopy facilities on site as well. So I'll skip over this one, but you can see just down the bottom right some more of that CT scanning that we're able to do on pouch cells, and able to see what's happening in the stack, the integrity of the welds, all of this, which is time saving and unable to argue against the data that is being generated. So you can see we've quite the scale of things in terms of the metrology for this. So kind of getting into the I wouldn't want to say meat of it, but hopefully something that's a bit more interesting is in terms of current battery technologies. Lithium-ion cells suffering from lower capacities. I'm sure that comes as no shock to people at higher C rates on discharge and charge, and this can increase charging times. And loss of overall capacity as you go. So carbon products, again, can add weight to the cell. People are normally putting in these carbon products to give better electronic conductivity, and that then helps in terms of your discharge capacity and keeping the overall capacity of the cell up. But if you're putting more of this in, then you have electrochemically dead weight in there, and this then reduces the energy density of the cell. Because you have to have it in there to make it work, you'd rather have the minimum amount necessary in there to get maximum performance out of the cell. New carbon products are being developed the whole time to be incorporated into the cell at much lower concentrations. While this doesn't, I suppose the next bullet points can be interpreted slightly wrongly in that it doesn't increase the theoretical capacity, it increases the capacity retention at set discharge rates. And obviously it lowers the resistance of the electrodes. So the conductivity that you get from the carbon additives that are being put in allow a reduction in the overall resistance, which then allows the retention of your capacity. Hope that makes sense. If not, please quiz me. It also gives a coating stability. So one thing that we love in battery manufacturing is if we can get 2 positives from anything that we're putting in. So you get a certain amount of compressibility and also coating stability from the kind of neural network that you're generating with these additives going in. This allows thicker coatings, and as you can go thicker, if you can retain the performance, then you've got, in a given thickness, you'll have less current collectors, so therefore you have more energy density. So you're heading in the right direction. It's all about people who would want an infinitely thick electrode with exactly the same performance as an infinitesimally thin electrode, and across the spectrum of discharge capabilities. Obviously, as you go thicker and you're starting to wind things for, say, a cylindrical cell, you can see cracking. A lot of these carbon additives, given that stability, will allow the coiling of an electrode, whereas without would just generate a lot of failures and cracks. As we see here, the high surface area carbons can provide better cohesion, which is what you want in terms of being able to coil them up and eliminating the cracking, which we do see quite a bit of without. What we have here is kind of a quick demonstration, kind of have to, unsurprisingly, anonymize quite a bit of this, is looking at carbon 1 would be a baseline, just a carbon black additive in, and carbons 2 and 3 are far more advanced, heading towards the carbon nanotube graphene school of thinking. And you can see a huge difference in terms of capacity as a function of C rate here. This is the same active material. You have a rough guide on the formulations down the bottom right. You're talking 98% active in here. And you see very, very impressive retentions across the different C rates. This is what I mean about the increased capacity. You're looking at the difference between 80 and almost 180 milliamp per hour per gram. The same thing, less than 1% of an additive in there, given this much of a performance boost. It really is impressive. And you can see, as well as this, you get the structural stability of the coating as well. This is just showing the kind of the first cycle versus 50th cycle dVdQ comparison. And this is looking at the polarization, and basically you can see that with just a normal carbon pushing at this type of a formulation, that the whole system is falling apart as between cycle 1 and cycle 50, and even at the beginning is still more polarized than that with the more advanced carbon additives in there. So you can see how you can enable not only the stability, but the performance as well as the rate capability. So it's not a matter of just whacking something down and going thicker and hoping it works. You have to be very clever with the additives that are going in there. And you can quite clearly see from the last couple of slides the type of performance that you can get out of these systems when you add these things in. Like I say, it's a very brief, I'm more open to the conversation around things. The lithium-ion technology offers limited scope the current lithium-ion technology, the new carbons that are being generated on these additives, on this like sub 1 weight percent of them, really are showing a lot of advantages in terms of energy densities, reduced charging times, stability of the coating, stability of the overall system. One comment that I make, and myself and Terence have been discussing, is it seems to be with these additives more along the lines of the carbon nanotubes than the graphene. And the graphene seems to not have the same level of confidence in terms of comparing apples with apples and what's a drop-in technology. It feels the carbon nanotube is that bit more predictable at the moment in terms of processing. And it just feels like a somewhat of a gap for a good graphene offering in this area, which would be interesting to look at. But you can definitely see the advantages that come from it. Hopefully you can see the advantages that come from it in my brief presentation here. So I'm happy to take some questions. Looking forward to a bit of conversation around that. Okay, thank you for listening.
Mark, and please include your contact information on a slide.
I will indeed.
If you could stop the share from your side, then we'll just get into like a Q&A format. Excellent. So thank you for the overview. It's incredibly impressive. The weapons that you have at WMG to work on this. It's a fantastic facility. So a very high level question is simply, obviously I know that there are people that would like to work with you that maybe are not already working with you. It seems like a lot are already working with you. Not that you need more to do, but if somebody wanted to, to collaborate or engage with WMG, how does one go about that?
I think it's make contact through the contact details that I would put on that last slide.
Okay, simple enough.
It's that, or they can go through, there's a business development contact on the WMG webpage. They can make initial contact there. That would be that'd be picked up and then probably brought to mine or one of my colleagues' attention as well.
And a couple of questions, then I want to hand off to my colleague Dexter Johnson, who's our chief analyst based out of Madrid. I know they'll have questions for you. And then if the audience has questions, please use the Q&A dialog box or the chat feature to pose your question. I know you had anonymized carbon 2 and carbon 3. The performance of both of those seemed to be extremely similar to one another. Were those very similar materials, or was there some difference?
They were pretty similar, different supplies that they were coming from, but yeah, fairly similar materials. Yeah.
Okay. And then one last question before I hand over is what you alluded to at the end, that we've talked about, nanotubes seem to have this reliability. There's been maybe a little bit more validation with them and such, and with graphene. Everybody who knows graphene, or at least from our side, understands that graphene is not one thing, but it's many, many things. There's hundreds of different permutations of it. So I think there's a challenge in that alone. The million-dollar question, is it because graphene does or doesn't work, or simply because we have had some handling, processing, consistency, right formulation type problems, and we just haven't hit the right formulation, if that makes sense?
I think it's the latter. To be honest, I'll go back. Sorry, Terence, on reference conversation in the past with you, but the ability to know what you're getting. There's so many graphene suppliers out there, and unfortunately, you get a few cowboys as well, and that can ruin the reputation of the vast majority. I think with graphene 2, it was seen as very high cost initially, and I don't think that's been completely dispersed. Dispersed being the next point I'll come to as well, is seeing some commercial offerings in terms of dispersions as well, and you're normally down at the 0.1, if not lower solids, and that means you're carrying an awful lot of solvent into a process. And as we head towards higher solids, people starting to talk about dry processing, et cetera, you don't want to be bringing solvent in. It's that processability against performance. And it feels like there's a little bit left to go there to get that. But I think as a material, it definitely has. I've seen some very impressive electrochemistry with graphene in there as an additive, be that coatings or in the actual electrode formulation. There's also a bit of the worry with graphene is that the second you start mixing it into a system, you end up with a very expensive graphite agglomeration. And it's just, again, it's the handling, the processing. It all goes back to that.
No, that makes perfect sense. And I know that we have both from the research side, in fact, a conversation just last week about a production method putting graphene into a slurry with very low solvent content, which was specifically for batteries would be quite interesting. And then the formulation side, I know we've got some companies with expertise in the inks that are refining that. So yeah, it's encouraging. So the point is there's a runway here, and there's a way to optimize the graphene in your systems. Sounds like. Yep. Dexter, let me hand over to you, Dexter, and then we'll take some also from the audience. Did you have some questions?
Yeah, I before we drill down, I guess you referenced the lithium-ion batteries that you work with. Do you work with alternative chemistries, and if so, what would those be?
Yeah, sodium-ion. Definitely, we have assistant professor Ivana Hassa as a high level. That's her background, that's her wheelhouse, is sodium-ion. And we do some work with supercapacitors as well.
Okay. And I guess then sort of drill down a little bit, and because some of the questions from the audience are good, and I think we should get to those. But you mentioned three carbons. I guess you kind of talked about two of them, graphene and carbon nanotubes. I guess we're talking about multi-walled carbon nanotubes. Is that right? Or is it both single wall and multi-wall?
Yeah, I think in terms of availability of carbon additives, you've multi-walled carbon multi-walled, single-walled, and I saw then there's even a comment on some like nanospheres of carbons and things like that as well. So there is a plethora in there really.
Okay, so that would be one of them. That answers one of the questions from the audience. Are you working with carbon nanospheres? And I guess the answer to that would be yes. I guess, could you give us a sense of how it breaks down in terms of how much work you're doing with looking at graphene and how much as far as these alternative carbons are concerned? Would you say 10% of the work you're doing is with graphene and 70% with carbon nanotubes, and the other 20% is with other kind of carbon materials? How does it break down?
It's a difficult one to break down. I would say at the moment, a lot of the advanced carbon additives that are going in are, as I said, the carbon nanotube side of stuff and carbon nanostructures. So when you start to say carbon nanostructures, then that's a bit of a blurry line in and of itself of what exactly is that. Something that we're trying to build up is more of a characterization capability, Raman spectroscopy, looking at DG bands on things to see how good the quality of the carbon nanotubes are. Does aspect ratio make a difference in what's going in there as well? Straight up with the graphene, it's a smaller percentage of the work at the moment, but I feel it's something that I'd like to collaborate more on going forward to get that processability, to get that concentration and dispersion up, and to show the viability of it. At the moment, it's more carbon nanotubes, multi-walled, single-walled, and trying to improve the overall performance of the system, and then baselining that against your usual carbon black additives.
Yeah, I hand it back to you, Terence, to take some of the questions from the audience.
Sure. So I'd layer in two questions together. One from our audience talking about, we've seen the benefits on the anode side. What about the cathode side? And I would just extend that to, where in the battery construction do you see these advanced carbons playing a role? And we've just been discussing graphene versus nanotubes, but what we've seen from research and from experimentation is a combination of nanotubes and graphene together actually perform better than either material alone. So I don't know if you've had any of those hybrid materials. And then the cathode anode.
Good point. Question. Yeah. So combination, different scale lengths works better every time. It's without a shadow of a doubt. Even incorporating some vapor-grown carbon fibers as well, because then you're covering the scale length within the system, giving different lengths of connectivity. So if it's graphene carbon nanotube plus graphitic particles, that definitely works. It works better than any one on their own. And it's both cathode and anode that this is working for. On the anode, I think with graphene, you're seeing people use it more with silicon additives, where you're looking at the strain of the volume expansion on lithiation, delithiation being somewhat mitigated by the graphene, and the ability for the graphene to almost move with the expansion to hopefully give more stability in the framework of the anode coating. But yeah, it's both sides. It's formulation of the slurry on the cathode and the anode, and with kind of phosphate-type chemistries, your lithium iron phosphates, which require a carbon coating to work, because their inherent bulk conductivity is so low. It has to have a carbon nanotube. I keep saying carbon nanotube. Sorry, Terence. It has to have a carbonaceous coating, because that gives it the electronic conductivity. Now, there's plenty of papers out there showing if you put graphene nanoplatelets around that and then anneal that, you get an even increased performance. So this is the active cathode material itself that you're coating. We're not going into the slurry. Now, the slurry, as previous comment, can look at both cathode and anode. You can actually enhance the active material itself as a powder with graphene coatings, with clever carbons, with mixtures as well.
Excellent. Excellent. I want to point out that we're very happy that Warwick is a member of the Graphene Council, and we really appreciate your participation here. I have maybe a closing question. We have time for just one more. Graphene producers and formulators have expertise with that material, but not necessarily with battery construction like you have, and vice versa, right? What is the best thing that the graphene community can do to deliver a better product that will see the light of day in battery chemistries? What do you need from the graphene producer side to make this work better?
A higher concentration of dispersion and quality, reproducible quality, and cost. Yeah. So it is that for processability, it's got to be a higher concentration. For confidence, it's got to be demonstrate reproducibility, and for acceptance, the economics have to be at a right point. And it's economics versus performance. So there is that. It's not like it's got to be the same as a carbon black.
Excellent. Excellent. Well, Mark, listen, I think we could be here all day talking to you. You're a tremendous resource. I appreciate it. I know you're exceptionally busy, which is totally understandable. So thank you for joining us. Thank you for sharing. We'll be in touch again. Obviously, this is a hot topic that's not going away. This is going to be just continue. This is so needed to solve these problems. So thank you so much for that. Appreciate your time.
No problem at all. Take care.
Be safe.
Okay. Bye now.
Okay.